In this video, I want to take a little bit of time to specifically address the subject of refractory period and its consequences for muscle contraction in cardiac muscle. To begin with, a reminder of what refractory period is. It's the portion of an action potential when it's impossible to generate a new AP, that portion called absolute refractory period, or when a new AP can only be generated with a larger than threshold stimulus, relative refractory period. Here, I'm mainly interested in the absolute refractory period. And let's just take a look at how refractory period in skeletal muscle and how refractory period in cardiac muscle matches up with contraction differently. So I'm going to put a couple graphs up on the screen. This top graph on the y-axis has membrane potential in millivolts. The line at the bottom is resting potential, and the zero value, 0 millivolts, is marked. Immediately below that graph, I'm going to put a second graph where the y-axis is muscle tension, increasing as we go up. Both of these graphs have the same x-axis, which is time in milliseconds. And you can see here I've got the milliseconds marked out in 100 millisecond intervals. Time 0 on the left represents the beginning of action potential. I want to start by putting skeletal muscle action potential on here. So there's our skeletal muscle AP lasting in the vicinity of a couple milliseconds. And here is its absolute refractory period. Below that, I'm now going to put the contraction cycle, essentially muscle twitch for a single action potential in a single muscle cell. And in skeletal muscle, this is the pattern we see. Because of that slight delay from when the AP occurs to when contraction actually begins, the absolute refractory period is finished well before the muscle really begins to produce very much tension. And what you may remember, the consequence of that is we can stimulate the muscle repeatedly on the way up to maximum tension. We can get this phenomenon of tetanus occurring, where incomplete tetanus can occur with repeated stimulation where the total tension increases, and complete tetanus can occur where we essentially see fusion and maximal production of tension in the muscle cell as a result of maximal stimulation. Now I want to look at how cardiac muscle is different. Here's our cardiac muscle action potential, and below that, or before we go below that, here's the refractory period. Now you got to keep in mind, the way refractory period is defined in both cardiac and skeletal muscle is essentially the same. Absolute refractory period essentially begins with depolarization and ends prior to the hyperpolarization phase. Because of the plateau, the equivalent endpoint in cardiac muscle is much later. So a large part of the cardiac muscle action potential is dominated by the absolute refractory period. When we put muscle tension on the graph here, on the bottom graph, you can see a very important difference from skeletal muscle. In cardiac muscle, the action potential occurs and absolute refractory period is not finished until the muscle has already started to relax. So the muscle contracts more slowly, the action potential lasts longer, and the result is, in skeletal muscle, tetany of the muscle, complete tetanus of the muscle is a possibility because absolute refractory period ends well before the muscle maxes out tension. In cardiac muscle, complete tetanus is essentially impossible because you can't stimulate the muscle a second time until it's already completed the contraction phase and is into relaxation. Imagine what would happen in the heart if tetany occurred, and you can see the benefit of this. This is an important advantage to the longer action potential in cardiac muscle.